Great. Okay, well, thanks. We're going to, let's see. So thanks to Natalie and Emily for the invite. We're going to shift gears a little bit here and focus on early industrial activities, depending on whether you think of flaking rocks as industrial or not. Anyway, it's very collaborative research, involves lots of people from various parts of the world. Always important to acknowledge your funders, so National Science Foundation, and then some of the work I'm going to be talking about today, specifically funded by the John Feld Fund at Oxford and All Souls College at Oxford. So about 25 years ago, the first measurements of lead in deep ice cores from the Arctic were published. And they showed that in the red, you can see on the red there that concentrations went up sometime during antiquity, concentrations increased and lead isotopes decreased. And that led people to think, oh, it's anthropogenic, result of anthropogenic emissions. And in fact, I was aware of these measurements, but I didn't realize that ancient historians and archaeologists were arguing in the literature about big issues, things like whether the Roman economy was stronger under the Republic or whether it was stronger under the Empire. And they were making those arguments on these 18 points, each representing 2 years. So on the horizontal axis there, that's 1000 BCE to 800 AD or CE. And so you can imagine it's, I was surprised they were spending so much time arguing about these 18 points. And so about 5 or 6 years ago, this guy, Andrew Wilson, and his colleague, Mark Pollard at Oxford approached me because I guess they'd heard through the grapevine what we could do with ice cores these days. And they approached me about developing a much higher resolution record and more continuous record of lead pollution during antiquity. So that's what we did. And this is the result of that. So instead of 18 measurements, we have 21,000 measurements, and we get about 12 samples per year on average during antiquity. And you can see that the records are in general in reasonable agreement, but our 21,000 measurements provide a much more complete picture of what's going on. Since this is not an ice core crowd, I thought I would give you a little bit of background on ice cores. Imagine you're standing on an ice sheet and in Antarctica or Greenland, it's maybe -20, the snow is falling, it's white, it's flat, you're standing on about, let's say, 2 to 3 kilometers of ice. And the snow's falling, it forms a surface layer, it starts to compact, forms an older layer, eventually turns into ice at about 100 meters, let's say. And then that's below that is where the gases and so forth are trapped. But not just, I mean, you can imagine that it seems like very clean snow, but in reality, in the air all around us are these little particles and droplets called aerosols that come from various natural sources, things like sea spray and desert dust, volcanic eruptions and wildfires. And then more recently, industrial emissions. And some of those particles are also deposited in the ice and incorporated into the ice, these layers of ice that are building up year by year. When we come along and drill an ice core through it, so depth is going down and time is going up. And you can imagine that allows us to sample this sort of layer cake of environmental history that's in very, like a VARD lake sediment record would be kind of the same idea. And so we got my group and a lot of our collaborators go out and collect ice cores in places like East Antarctica. This is with the Australians. And we bring the cores back to the lab and analyze them. But one of the earlier, I think it was Eric who talked about decontamination and the issues associated with decontamination. And that is a big deal when you're trying to measure trace metals in very old ice. And so you might ask, well, why were there only 18 measurements made 25 years ago? And the reason was because that in order to get clean samples, Rossmann and Hong and so forth and their colleagues in France spent vast amounts of time mechanically decontaminating a chunk of ice. So you can see that piece of ice there in a laminar flow hood. Guys are all in clean room clothing and so forth. And they are slowly mechanically chipping ice on that lathe. They're slowly chipping the ice off in sequential layers, which they're going to analyze. And we get to the middle, the ice that hasn't been exposed to any handling or anything like that. Presumably that's the cleanest part. huge amounts of effort. I really admire the efforts these guys went to. We have, in the last 15 years or so, kind of changed that. And we, instead of using mechanical decontamination, we use a melter to decontaminate the samples. So you can see that 3 centimeter, that ice core right there on the right-hand side. It's about 10 centimeters in diameter, and we handle it in sort of 1 meter chunks. When we get it back to the lab, we cut out of it these longitudinal sticks. Okay, they're really, the sticks doesn't sound very technical, so let's call them longitudinal samples that we cut from the ice, and we can cut up to 7 parallel sticks from one of these 10 centimeter cores. And we clean the ends very carefully. You can see down there on the lower right, and we load that stick of ice, or that longitudinal sample of ice, up into a melter that we developed, and that's in a cold room. And the ice just falls down by gravity onto this heated melter plate that's made out of ceramic. And so we can clean it with concentrated acid and so forth. And we split those ridges that are engraved into that melter plate, split the melt stream into different sections. And the part that we measure these things like heavy metals on is only the innermost 10% of that cross section. The next 20% we might use for more abundant things or water isotopes. And then the final outer 70% we throw away as potentially contaminated. So we're very aggressive, much more aggressive than any other lab in the world about what part of the ice we keep. And that's why this decontamination using the melter that allows us to do 21,000 measurements in a month instead of 12 measurements in 3 or 4 years. So it's really changed things, revolutionized things in a lot of ways. I'm going to talk about 2 fairly recently published papers. The first one was published in 2018 in Proceedings of the National Academy. But before we go there, let's ask a couple of questions. Well, what can Greenland lead pollution tell us about ancient economies during antiquity? First of all, who cares? As I mentioned, these ancient and economic historians and archaeologists, political scientists were using those 18 points to have lots of discussions in the literature. But also environmental scientists and epidemiologists, because lead is a neurotoxin. And then you might ask, well, how does lead connect to ancient history? Well, it turns out that almost all silver in Europe and in many parts of the world, but especially in Europe, silver occurs in lead-silver ores. So for every ounce or gram of silver you're going to produce something like 10,000 grams of lead. Lead has a lower boiling point. It's going to boil off. Some of that lead's going to end up in the atmosphere and get blown up to Greenland or in other parts of the Arctic. The other advantage is, another nice thing about lead is has pretty low background levels. So that, if you will, the signal to noise, the anthropogenic signal to the background noise level is quite good. And then finally, the instruments that we use have very, very low detection limits in the order of part per quadrillion detection limits for lead. So I know I'm preaching to the choir here, but what are the 3 most important words in paleo-environmental studies? Since we don't have we can't do a Socratic method here, I'll tell you. So it's dating, dating, and dating. And that dating is especially important if you're going to try to infer causality. So instead of correlation, you're going to try to infer causality. You better make sure your dating is correct and that it's independent. This is an example. We use annual layer counting. So we just started the date at which the ice core was collected, and when we measured all these different chemicals, about 30 different chemicals and elements in the same stick of ice, that same little piece of ice. And almost every one of those chemicals or elements has an annual cycle in it, it turns out. So we just count those annual cycles. So this is just an example, very much like a tree ring or a barbed lake sediment. This is an example from 380 to 380 meters, 381 meters in the North Group 2 ice core from Greenland. And you can see that I've picked the years. So this is 2,000 years ago. And you can see it's the annual dating is pretty darn clear in this ice core. Of course, any process like that, you're going to accumulate error. And so we spend a lot of time, don't have time to go into it here, but we spend a lot of time trying to evaluate the accuracy of our chronologies, of our ice core chronologies. So we compare to things like both low frequency and high frequency changes in cosmogenic isotopes and things like that. Bottom line is that we, based on these comparisons, we think that our age uncertainty in antiquity is less than plus or minus 2 years. And in fact, based on comparisons in volcanoes and things like that, it appears that we're spot on at 43 BCE. So we're pretty happy with our age scales. As I said, we spend a lot of time on them. Another thing we have to think about is lead provenance. So that would be, so archaeological and historical history suggests that the possible sources are in Europe or China during antiquity. We can use isotopes, and I'm not going to talk about that, but people do use isotopes, and we have a postdoc starting who's going to measure isotopes through this whole ice core. But the bottom line is that the history and the archaeology suggests that the sites in China, in Asia, would have to be, well, here, I'm getting ahead of myself, sorry. Keep in mind that the Roman era sites, any sites that are in Europe or in China, would be a long way from Greenland, so that long-range transport is implicit. To address that, we use very sophisticated, the state-of-the-art atmospheric transport and deposition models, in this case called FlexPart from Norway and Austria. Again, I don't have time to go into it, but this kind of modeling suggests that yes, we could be seeing Chinese lead in Greenland, but the ice core site is about 10 times more sensitive to European emissions than it is to Asian emissions. So if we are seeing Chinese lead, the emissions has to be enormous, and there's no evidence to suggest that they're that large. The other big advantage in using this modeling is that we can turn deposition in a Greenland ice core, annual deposition in Greenland ice core, into a pretty constrained estimate of the emissions, atmospheric emissions from Europe that would be required to generate that pollution. So in this particular case that I've identified on there, that 0.75 micrograms per meter squared per year of lead pollution in Europe, in Greenland, would equate to about 1.8 kilotons per year of lead emissions from Europe as a whole. So let's take a look at the record. So this is what the record looks like, our 21,000 measurements, going from 1100 BCE on the left to 800 AD on the right. And it spans the Iron Age through classical and late antiquity into the early Middle Ages. You can see that initial increase back there, not very large increase, but that initial increase correlates to Phoenician expansion in the 9th to the 5th centuries. And then you can see there's sort of a big jump up, but in general, a very pronounced bump associated with classical antiquity, and going into late antiquity, but mostly in classical antiquity. And you can see there are a couple of big bites out of it. I don't know, can you see my cursor if I move it? Can you see my cursor? Yeah, so there's a big bite here and there's another big bite here. Well, it turns out that those correspond exactly to the crisis of the Roman Republic and the 3rd century crisis. In between them is the Pax Romana, and our data would suggest that the Pax Romana was a period of stable and high lead pollution, indicating a pretty stable and strong economy. One of the things you can notice is that there's the Pax Romana the lead pollution, the high lead pollution starts a little while after the start of the Pax Romana and ends a little bit before the end of the Pax Romana. And you might wonder what that is. And it turns out that it took Octavian or Caesar Augustus about 9 or 10 years to establish administrative control and pacification of Gaul and Iberia, where these emissions are coming from. And so that explains that approximately 9 or 10 year offset between the start of the Pax Romana and the start of the Pax Romana and the big increase in lead. At the other end, you see this, that's when the Antonine Plague hit. So the first incidence, I guess, of smallpox in 165. And lead pollution in Greenland dropped immediately as soon as the plague hit. There's also another dip in the plague of Cyprian, the other of the 2 big plagues during that period. let's see, so to bring it back to the economy, so this is a comparison in red. That's the fineness of silver in Roman coinage, the denarii coins or denarius coins. And you can see that the fineness of the coinage follows the lead pollution signal down very nicely. They parallel each other beautifully. And in fact, at the nadir there of our lead pollution record during the plague of Cyprian, that's when Rome abandoned silver coinage and shifted to, I guess, a bimetallic, a bronze and gold coinage system. Let me then talk a little bit about the second paper, which was published in 2019, also in PNAS. And in that paper, we extended a lot of this. Jump on? Yeah, we extended this from antiquity all the way up to the present. And instead of using a single ice core, we use an array of 13 ice cores from around the Arctic. It's a very broad array in terms of it represents about 150 degrees of longitude. So it represents nearly half of the Arctic. And we're going to, again, because of that very broad scale, we're going to again use the FlexPart atmospheric modeling to interpret the record. If we just for ease, let's combine the South Greenland ice cores, the North Greenland ice cores into one composite each, and then compare them to the Russian Arctic. And what you see is on the right-hand side there, and that's the record that we get over the last 2,200 years. It's a little hard to see in that sense, so let's look at it instead on a logarithmic scale. So the same graph on the, as we saw a second ago, on the left, and now on the logarithmic scale on the right. What we see is a 300-fold, talk about a human trace, we see a 300-fold increase, not 300%, but 300-fold increase in lead pollution over this vast range part of the Arctic since starting around, and that 300-fold is since the start of the Middle Ages, about 500, up to the 1970s industrial peak. One of the first things you notice is that the Russian Arctic level of pollution is quite a bit higher than the two Greenland records. And that makes sense. That can be explained, that's consistent, I should say, with the atmospheric modeling, which suggests that the Russian Arctic, because of the westerlies, the Russian Arctic is about 5 to 10 times more sensitive to emissions from Europe than the Greenland ice core sites are. The other thing you start to notice is it's a little bit hard because at least on my screen, you guys are on top of that. Let me see if I can pull that over. Yeah. So you can see that there's a lot of common variability all the way across this sort of half of the Arctic. And what starts to, you start to look at things, you can see again, the Antonine plague there, you can see the plague of Cyprian in both of the longer records. You see, for instance, the drop associated with the Black Death and the Great Famine. And then anyway, lots of common variability, as I say, and a lot of it linked to known historical events. What's going on here? So we can take that, because these records are continuous and the ice cores or the glaciers have acted as objective recorders. We can actually look at growth rates and try to, if we think of lead pollution as a proxy of industrial GDP, we can start to look at growth rates. And let's just, for the interest of time, let's just look at the black one from the Russian Arctic. We can see that the growth rates were pretty high. I mean, at least talking to my colleagues, they seem to think that's a pretty high growth rate for the early Middle Ages. The high Middle Ages were only a little bit higher. And then you get to the start of the late Middle Ages and everything flattens or declines and really doesn't resume an upward climb until the Enlightenment around the start of the 17th century, 18th century. And then growth rates are quite rapid. And then of course you hit the Industrial Revolution around 1850 and the growth rates really jump up. Let's see. And so what's really happening here, if you look on that graph on the other side, on the right-hand side, what's happening is that it's, again, the plagues are playing a big role. So that during the early and high Middle Ages, there weren't a lot of pandemics or plagues. at least not major ones. And then you get to the start of the late Middle Ages, and that's when the second plague pandemic starts and starts pounding Europe with lots of death. and so what you see is those very pronounced drops, starting with the Great Famine, but then really accelerated during the Bull Black Death. Let's see, and then things grow, and then you can see the impact of some of the cholera pandemics and things like that. By the way, you can see that big drop there, just recent drop. So the good news is about lead pollution since the implementation of things like the Clean Air Act in the US and similar legislation in Europe have resulted in about an 80% drop in lead pollution in the Arctic. So that's the good news. The bad news is that you're still 60-fold above where you were at the start of the Middle Ages. So, So just in conclusion, I hope I've convinced you that ice core records can contribute to historical and archaeological research. The ice sheets act as objective recorders, so it doesn't depend on somebody writing something down or a document surviving to the present or whatever. I would emphasize that understanding atmospheric transport and deposition is critical if you're going to try to interpret these things quantitatively. Of course, dating. And then I didn't talk about it much, but it's in the 2019 paper. Social unrest, famine, and climate all seem to play a role in lead pollution in Greenland. But it's really the plagues that seem to have, pandemics that seem to have had a big impact on ancient and medieval economies. And then in terms of plans, what we're doing next is extending this. We've been funded by NSF to extend this back, well-dated records back into the Bronze Age using an ice core we were supposed to collect in 2020 and in 2021, but have been delayed because of COVID. And so now we're hoping for 2022. And then also we've used another ice core that's not quite as well dated to extend these records back into the European Neolithic about 5,000 BCE. One last thing I wanted to mention was that part of this NSF funding is to have, this is an outgrowth of a workshop I taught at Princeton, bringing natural archives, the idea of natural archives and the understanding of natural archives to ancient historians and archaeologists. And so as part of this NSF grant, we're supposed to have 2 of these consilience workshops, and the idea is to bring especially young investigators to our lab and have them participate in ice core analyses and things like that, and kind of interact with my group. This was the group, this is a prototype class that we did with Joe Manning and one of his classes at Yale in 2018. This guy over here is a numismatist, and this woman is a Latinist, and I can assure you that it's the first time a numismatist or a Latinist has helped analyze an ice core. So thank you.